Hey guys, what's up? Eddie Aho here with KissAnalog.com. Alright, today's kind of an exciting day because we're actually going to start designing our power supply. And we're going to start with the PFC. And then we'll go back through the stuff between the PFC and the input power cord. And then we'll go the other way to the second converter where we get our isolation and our output voltages. But we'll start with the PFC, okay? And just for fun. So this thing here is an eval card of a PFC close to what we would want. Now, unfortunately, and this is a Texas Instrument, I really like this particular chip because I've used it and it's worked great. It's pretty easy to use. Problem is can't get them right now, and that's a big problem with today. A lot of things I'm designing at work and stuff, we have to check to see what chips you can get your hands on because a lot of things just aren't on the shelf anymore. So, and you want quantities because you don't want to design something and then have, not be able to get it down to, 6 months later. So, and it's pretty hard to predict that also, but we'll look at some chips here, and if we see large quantities, like I'm talking thousands, then chances are they'll be around long enough for, at least us to buy them so we can do our project. And then hopefully the shelves, the bins start filling up and this problem takes care of itself. But right now it's a problem. So I'm going to take you along and show you how we're going to select a chip, okay? But I want to show you this board just as an example of what we're trying to do. It's just a boost regulator. The control IC is specialized because the waveform that we get in that comes in off this bridge rectifier is a pulsating DC. We don't use a large capacitor to store, but we use a small one just for filtering and to supply that inrush current when the MOSFET is switching it. And that's another thing. We're going to select the frequency. Now, what I can tell you is, a lot of times, especially people that aren't really familiar switching power supplies or have some familiarity, you might think, hey, we're going to switch at hundreds of kilohertz because, the understanding is it makes things really small and, that's the cool way to go. Well, with PFCs, because we're dealing with, the kind of waveform we're dealing with, you don't normally switch that fast. And also it's a high voltage. We're going to put out probably 390, 400 volts on the output, okay? So it's a lot of voltage to be switching. One common frequency is right around 60 kilohertz. And one of the reasons why, now write this down, this is an important thing, is if you ever go through EMC testing and there's a curve that you have to, all your noise has to be below, okay? As the machine scans that, right around right at 150 kilohertz, it changes resolution and the curve changes. It kind of drops down and it gets a little tougher. So if you switch at 60 kilohertz, that switching spike is in the easier zone. 150 kilohertz towards 0 hertz is the easier, is the higher part of the curve, which is easier, okay? So you're saying, well, why can't we switch at 120K? We're underneath 150. But here's the other thing. Here's the other kind of magic that happens. When you switch at, say, 60 kilohertz, the second harmonic is what? 120 kilohertz. So you might have a decent spike at your second harmonic as well. So your fundamental 60 hertz and your second harmonic 120 hertz is underneath the 150K thing. So you're kind of getting a freebie. Well, you're getting a little ease of your EMI testing, your filtering by doing that. So that's one reason people switch there, okay? There's two common frequencies that a lot of chips are using, and I think it's because when they design the chips, they can double the frequency of the oscillator fairly easy. And so it gives you two frequencies to choose from. A lot of these chips have one version of the chip that will switch at 60 kilohertz or 62, 64 kilohertz, somewhere around there, and the other chip will switch at twice that frequency. So a lot of chips have a selection of those two. Some are variable, you can set the frequency where you want, but I just wanted to kind of throw that out there. When we're going to select chips, if you know that you want to switch at a certain frequency, then you can look for that when you're selecting chips. First thing we're going to do is we're going to try to find the bins with the most parts in, and then we'll go and we'll get picky after that, okay? So that's one of the things you look for when you look for a control chip, is the frequency you want. The other thing you look for is, and I'll tell you, there's some cool things that some of these chips do, but really the big thing is this switching frequency, which these kind of chips, they're all going to provide frequencies that are usable. So that's not really a big deciding factor unless it's something you've already selected that you want, then that's what you're going to look for. So not all chips are variable or selectable. You know, you have to pick the frequency of switching you want. The other thing is the drive. When that signal leaves that chip and turns that transistor on and off, can it do it by itself, or does it need a drive chip? And that's kind of a pain in the butt if it needs a drive chip. So it's nice to select a chip that can actually have enough signal, say 1 or 2 amps, that can actually drive a decent sized FET. Because the FET that we're going to have on here is going to be a high voltage FET. Now, when you're trying to choose FETs, a lot of times when you're choosing FETs around 40 volts for a lot of things that we use, automotive things, the RDS-on, a lot of the characteristics of the MOSFET, a lot of the parameters are just awesome, because it's a low voltage FET and they can do a lot of cool things. When voltage gets higher, like say 600 volts, 650 volts, or even higher, because we're going to want a 600 volt FET, I think, or higher. And when you get a FET that big, internally you can imagine that the structure has to be designed differently, because you can't have arcing inside the stuff that makes up your FET, right? The semiconductor material. So the structure of that FET has to be designed such, for that high voltage. Well, then what happens is you end up higher capacitances, because you got, usually the FETs grow, the silicon grows in size for the higher voltage, and when that happens you get larger surface areas, which means higher capacitance, which that works against you big time, because now you got high voltage and higher capacitance, so that's not a good thing. Luckily for us, these FETs have come a long ways. And here's the thing, here's a question to you guys. Do you mind spending, say, $1, a couple of dollars, even $5 for a good FET, or spending a little bit more for a better FET? Spending a little bit more for a GaN FET, so we can have a cool GaN in here. So if we want to put a GaN FET for something like this, here's another option. Because we are switching to the little bit lower frequencies, and we could do a SiC, a silicon carbide FET. Those are really great. So we're going to talk about those options in the next video. We're going to select I think it's in the next video we're going to select the FET, okay? And here, let me just show you something. I got a board here. Alright, so here's my board, guys. Kind of just stir it together real quick here. And I'm going to write this stuff up, and my patrons, I think I'm going to provide them a nice PDF copy. Maybe I might even publish it in Amazon, self-publish it or something like that, chapter by chapter, for a PFC design. I've thought about that in the past. Years ago I was going to write a book, and I started to a number of different times, and then more and more authors came out, and I got less and less interested. But anyway, maybe I'll do that, and then But yeah, so here it is. So here's our circuit. Yeah, pardon my drawing skills. And I kind of numbered each one of these parts. This is our rectifier and our small cap. But here's the main parts, the ones that have numbers on them. We have a control chip that's driving this FET on and off. And I'm going to go over how these work again. And I'm going to also put some links down below. I've kind of walked through how PFC works. And I've got a couple videos, I think, on that. On this eval card, as a matter of fact. I even have some waveforms I've shown. But, okay, so we're going to drive this FET. And this inductor is the thing that's charging up and providing us the current. Okay? And then we have this diode that's really important. And that diode, I'm going to tell you right now, it's probably going to be a silicon carbide, okay? And we'll talk about why. And then we're going to have to come up with the C out, what size of capacitor. So on a normal low frequency pulsing power supply that some people call linears, that power, we'd have a big old bulk capacitor over here. But now what we do is we do this high frequency thing, and then we charge up this cap, so it can be a little bit smaller. Alright, so here's kind of the flow I put down. It doesn't have to be this way, but I said, okay, we're going to select a control chip. That's a good thing to do when you start, is find out the brains. Like, once you got that, everything else kind of gets centered around that thing. Alright guys, and there's another really important thing about this chip that we're going to be looking for when we go look for a chip. I'll show another board on that just in a moment, but we're going to just choose this control chip, and then we're going to select the frequency we want to switch at, okay? And then we're going to design our inductor once we know that stuff. And then we're going to come up with the FET. We're going to figure out how much current's going through it, and we're going to figure out the parameters that we need to know so we can select this FET, okay? And that'll be another video. And the PFC inductor will be another video. So each one of these steps, what we're going to do today probably, well, we'll see how far we get. Because this control chip's what we're focused on. And there's a question I have on which control chip you guys think we should have. We can vote on this stuff, because I want you guys to be involved in the design process. And so yeah, then we're going to select this diode. And that diode is going to be fairly easy to select. And then we're going to calculate the capacitor, how much capacitance we need. But yeah, we'll figure out the current, and then we can select that diode. Okay, so that's the main pieces of the PFC. All right, so that control chip, there's actually several different ways that control chip can operate, and let's talk about that. Alright guys, so here is another board I want to show you. Now these are the waveforms of the current through the inductor, okay? This one's continuous conduction mode, so there's always current in the inductor. So it charges up at some point, it's been running for a little bit, then the FET turns on, so it charges up the inductor, turns off, discharges, but then it turns on again, and it continues. So the inductor is has enough inductance that it can store the charge, and it can be above this line here. So you have this percentage of ripple that you decide you want. All right, now, and that's going to be based on your minimum load, your maximum load, your input voltage range, okay? Well, okay, the other selection, and it goes by different names, but boundary conduction mode or critical conduction mode, and that's where the current charges from 0, comes down to 0. There's a detector in the chip that determines that it's discharged, the inductor is fully discharged, and then it charges up again, discharges. So the frequency is not set on this, it varies a little bit. So because it's going to let this fully come down and discharge, and then it's going to say, okay, go ahead and start another pulse. And so the advantage of this one is, one thing, besides the discontinuous mode, where there's dead space in between, it's not a good usage of the inductor, and the ripple's high and all that stuff. Well, this one, better use of the inductor, so now there's no dead time where nothing's happening, where the inductor's dried out and nothing's switching. This one you automatically get another switch cycle, and so it's a little bit better operation, a little faster performance. But here's the thing, is because the inductor is able to discharge and charge fully, and if the frequency is similar to this, it's gonna vary. But if it's centered around a similar frequency up here, then that comparison, these current spikes are going to be much higher. Now, the advantage of this is that the inductor can be smaller, it can be less costly, and the disadvantage is you have really high current spikes. Okay, so the current ripple on this is a lot higher than here. The disadvantage with this one is you need a bigger inductor. The inductor's the most expensive part of the PFC. Okay, so that's why they've come out with these different modes. Now, these are just the two main ones, and then there's variations. Okay, and then on top of the variations, for instance, one of them is, well, it'll let you change the frequency, but not too much. It's got a boundary condition, so you can set the max or min frequency. Okay, but there's other ones where you can interleave. You can have two outputs tied together, so you can interleave them, and you can get some advantages there. And so there's variations on these two themes, but these are the main two themes. Okay, and this is probably the common one, especially when you're running higher power, which means the inductor even has to be bigger, has to be able to handle all that power. But compared to this, these currents would be just too much. So this guy here, for what we're doing, over say 100, 200 watts, you kind of want to go this way, I think. Or you can do some of those other fancier things where you have two interleaved converters, but then you have twice as much stuff. But it is a nice way to go. But this too, it works great. And at our power level, now if we're going to even 800 watts or something higher, then we might try some other topologies or even cooler. But this one, for what we're doing, is going to work great. It's going to be a great PFC. Okay, so let's go find a chip. And we'll be looking for one that does this. Alright guys, so this is a good example of a PFC. We have the input here, a fuse, and there's a little varistor here, and then we have our X caps and our comm mode choke. And these are the Y caps that work with this. Then we have an inrush current, an NTC for inrush current limiting right here. Alright guys, this is the UCC 28180 EVM eval card, and it puts at, it's 360 watts, so it's pretty close to what we would want. So we could do something very similar to this. Now it has this heatsink here, which we have the bridge rectifier mounted here, and there's the diode and the transistor up here that are switching, and then we have our volt capacitor for the output. And this is our PFC inductor, and we have a capacitor here on the input. So there's that. And then over here on the other side, so then on this side, we have our control chip with all the supporting circuits, your resistors, capacitors, and so on. So yeah, you can see it doesn't take a lot of circuitry, input filter, and PFC. So we would want to find something similar to this, I think. Alright guys, so I've searched on Mouser.com, and you can see this right here. I searched for semiconductors, power management ICs, and really what I was searching for is PFC, power factor correction. So I'm down here, and it says 503 results. And so we've gone through these filters here, and you can filter some more, and you can filter through companies, frequencies, different things, but let's just come down. And what I'm going to also do is click this box right here, in stock. So I don't know if I have to hit apply filters, but I will. Okay, so now we don't have to worry about the ones that are not in stock. And right off the bat, we have a non-semiconductors, the NCP 1680. So there's over 2,000 of those in stock here. That looks like a contender. Now I'm looking to see if it says continuous conduction mode. I didn't see it in the description, so we can go look at that chip. But let's just go down and just kind of see what we see. So that's the same chip, different package, or maybe one's on a rail and one's in a tube or something, you know. But look, 2,000 of these in stock, so it's really the same part. I believe it's probably the same package and everything. Okay, both over here doesn't really help me. So yeah, we'd have to pull up the data sheet, but before we do that, let's just look. Now, one thing is prices, and quantities of 10. You know, it's $6 for this chip, so it's fairly expensive chip. Now here's one, quantities 10 to 270, and it's a CCM, so that's what we're looking for. And it's got 1,400 in stock. So also another good company, ST Microelectronics. So the L4985 looks like an option. And you notice that's only an 8-pin package. Up here they didn't say, but 8-pin packages are fairly common for this. I'm not sure what this is. I think that's a different kind of product. It's $400. It's not a control chip. More ST Micro, so it could be the same part. It's got the same part number. One's an A and one's a B. That could be the frequency thing. Let's come over here, and I don't see. They didn't indicate that. So let's come down, just see what else we see. And these prices are better than the parts for the ON that we saw above. Now here's another ON, the NCP 1618. And it says, shoot, it doesn't say which kind of controller it is. So we'd have to go look, but again, 2,500. And look at this, quantities of 10 is like $1.19. So it doesn't surprise me that ON would have a really good price on a part. So ST Micro, now look at this, totally different part number. And also look how many pins there are on this. So this says it's a digital combo multi-mode PFC with LLC resonant controller built in. Now, I'll talk to you about this later, but I'm not a big fan of one chip that does two different converters on it at the same time. And just quickly, the reason why is you get two different frequencies switching, and I've experienced some issues with that before. So anyway, here's another one by Monolithic Power Systems, MPS 2500. And look at this. This one says CRM, so discontinuous mode. So we know that this is not what we want. This is for low power. These guys specialize, I think, in a little bit more lower power stuff. So that doesn't surprise me that it's that type of chip. But very inexpensive, and they've got lots of them. On semi with another one, hybrid, SICK, ILPFC. Look at that big chip. And look at the cost of this. This is probably some really cool chip that has some stuff built into it. And it looks like it probably has a SICK diode built into it. Might have the FET built into it. So, but there's only 90 in stock, and they are pretty pricey. So, yeah, I mean it. Anyway, that might be kind of cool to open it up and take a look at that chip. Infineon. Now look, here's ice. We like the ice stuff, right? Ice 2PC S05G. Now I know there's variations on this part. Look at this, 23,000 in stock and only $1.56. So this is definitely a contender. I'm pretty sure this is a CCM part, and that's what we want. And I'm just scrolling over. Got a lot of these columns are not really filled in. We're starting to see some information in them. Like here's a frequency down here on this one. Okay, let's go down. Power integrations. 110 watt. This has a FET. This has parts built into it. So this has a FET built into the package. So the price is a little bit higher, but still, you know, really inexpensive. I mean, you'd pay more for that than for the FET. So, wow, we might have to take a look at this. This is, and there's 1,800 in stock. So that's definitely a contender, I think. Rome, another 5,000 in stock. And look how inexpensive. Yeah, these are really inexpensive. They're under $1, so that's a contender. Infineon. Of course, we've been looking for an Infineon part. Okay, there's part number there, 5,000 in stock. Again, under $2, low price. So we'd have to check to make sure that's a CCM part. I mean, some of these I'm familiar with, some I'm not. Like this UCC part, Texas Instruments. Extended EP, I think that's extended package, so probably have extended temperature range on that, and that's probably why the price is a little bit higher too. And they can go up to 250 kilohertz. It's probably not a fixed one, it's probably one you can select. Unitrode has a number of these chips actually, and Texas Instruments. Texas Instruments bought Unitrode, but that's where the U comes from, is Unitrode, who was a big power company. So now this was 2,400, still not bad. And this is a buck control. You see, this one's a buck. I didn't recognize that number. That's probably why, because yeah, we don't really want a buck. We want a boost. Okay, looking at this one, 3818. It's a pre-regulator, bi-CMOS power factor pre-regulator, they call it. But yeah, it's okay. So just another chip to maybe look at. Here's almost 2,000 of this one, and it's, yeah, okay. And here's a LM. So Texas Instruments bought National Semiconductor too, so that's where the LM comes from. So that's another reason why they have so many parts, because they have different companies they bought, and they all had their own power factor chips. So this is another one that we could take a look at. There's quite a few in stock, so that's good. Power integrations again, and again, it looks like I think they've got some parts built into these, so 2,000 in stock. That's something to maybe look at, okay? And just kind of scrolling through, and we see some more. Here's Renaissance, which is Intersil. Intersil, that's why the ISL, they bought Intersil, and that's their part number. So this is a really good chip. I've used the little brother of this one, the 6730. And actually, I have a new design with this chip. But here we go. It's just over $2, 1,400 in stock. And this one operates at 62 kilohertz. And that one is a fixed frequency, I can tell you. It's not selectable. Okay, let's go down another page. Okay, wow, look at this. 12,000 in stock of this guy. This is a power factor correction PFC. Okay, this is a boundary mode. That's what we don't want. But man, look at all the ones in stock. And it's only $1.20. So I'm just going to scroll down and look for large quantities. Here's large quantities. Here's ICE 2PC. So this one, you know what, guys? This one is a serious contender. I think it's a CCM. I'm familiar with this ICE series, and 14,000. That's great. So let's keep that one in mind. And here's another power integrations with 1,000 in stock, and it has, I believe it has the FET built into it, 600 volt FET, which is pretty crazy for that price. Here's 19,000 of the ICE chip. Now, when we look at these two ICE chips, you'll see the part numbers are a little bit different. So, I think it might be frequencies. Let's come over here and look. See, this one's selectable from 50 to 315K. This guy down here is 70K because I think it has some other options. So they gave you only one. They didn't give you a selectable frequency, just a fixed frequency, and there's some other options. So, but in both cases, there's, quite a few, over 10,000 for sure. So I'm just kind of scrolling through. Here's 18,000 of this Diodes Incorporated one, and look how inexpensive. Wow, that's really inexpensive. I think I've looked at this guy, and I think it's going to be another, the discontinuous mode, so the critical conduction mode, whatever we want to call it. So I don't think it's going to be I don't think it's going to work for what we want, but we can open up the data sheet and take a look. Now, here's another one, 1606 power factor. This is from On Semi, and 23,000, and look at that, under $1. So this one here, 70 kilohertz. So man, the 1608, maybe that's one we need to look at too. Now here's these power integrations, again 600 in stock, and these power integration chips might be something really interesting to look at. Okay, just looking for large stocks. Let's go one more page. I'm just kind of giving you an idea. I want you to kind of look through this on your own and see what you guys think. Here's 8,000 this part. Now, see this right here? Here's something I want to point out. See when I hover over that, it says not recommended for new designs. So when we see this, we don't really want to design with that chip. It's great for people who already have it, in the design. It's probably got like a year left on this design, then we won't find it anymore. Kind of like this one down here. See, it says end of life. So these end of life ones, we want to kind of stay away from. All right. Yeah, I'm kind of interested in these power integration chips. There's not a huge amount of quantity though, but that's an interesting company and what they do, how they package FETs in with their control chip. All right, so let's go look at a data sheet for that inner seal part, the one I've used before. Okay guys, so this is the Renaissance part, the inner seal, used to be inner seal. That's why they have the I in front, because that was the inner seal part. But there's the A and B version of this guy. And let's see. Let's take a look, see what it is. I think the difference is the switching frequency. So see, look, here's CCM. That's what we want. Excellent power factor, THD over line and load. Okay, so this is what we want, something really clean. I think that's what we're going to get with the CCM type. And just look and see what else. There's some app notes over here. Now here's the, here's the A, and there's a non-skip and a skip type of operation where you can, and if you want to skip a light load, you get a higher efficiency. If you don't want to skip, you're going to get not as quite high efficiency if you don't skip. Okay, there's the simplified schematic, which is really not all that simplified. It's got most of the parts there, it looks like. Okay, here's a description of each pin, what it does. Okay, so, obviously you have a ground, you have a current sense. Compensation, that's for your voltage feedback. a VN pin, of course, and this is a brownout pin where you can select, the voltage where you want it to drop off, stop operating. Over voltage protection, here's your compensation that goes with your voltage feedback. So this I-comp is for the current feedback. And then here's your feedback pin, your skip, whether you're going to let it skip or not, and a regulated output, VCC, and your gate drive. So fairly simple, not a whole lot of pins. This one has more pins than its predecessor that had only 8 pins. Here's the temperature range of the part, and look, here's the A version, 124K, B version, 62K. Now here's a block diagram, okay? So, here's our basic EMI filter, our bridge rectifier, our small cap. Now this has a little high frequency filter, LC filter. That's why there's 2 small caps in this inductor, which is not a bad idea at all. It switches out the high frequency, so yeah, maybe we can add something like that. Here's a current sense resistor, and this line right here comes down here to the current sense. So this is the current sense function, this top left corner. Okay, then we come across here and we see our switching FET and our inductor, and those 2 guys work together to give the PFC action. And so come down here and you see the gate drive output. So top right corner is your voltage, your VCC, your voltage regulator, and all that stuff, and your gate drive. And here's gate drive ground. Okay, so here, these are the resistors for your over voltage protection, and then that comes off the output, and then it also has the feedbacks into this guy. So this is just setting a threshold where it's going to say, hey, it's over voltage, turn off, and this is your feedback control. Now here's compensation down here, and see it ties into your feedback control right here. It's just down here at the bottom. And here's your skip clamp, so you can turn this guy on or off depending on how you select this. And over here we have the brownout. So this cap's going to have a little filtering, but it's looking at the input, and when it doesn't see the right input voltage, it says, hey, we're in a brownout, and it comes in here and tells this guy. So now look at this thing. Here's our current sense coming in through here, and all this stuff's tied to this guy, who is your I compensation. So see these diodes up here? They come down here into this voltage divider, and this is where this guy can sense what's going on at your input AC voltage, and then it works with the brownout. And so yeah, there we go. So you can see all the stuff inside here. I mean, sure, there's a lot of stuff going on, but at the same time, it's pretty cool. If you break it down into functions, you can kind of see what's going on. Soft start right here, it's part of the current compensation. It soft starts it, so it starts up slow, is what that soft start does. So it doesn't just try to turn on that full blast when there's not enough voltage yet. So it kind of helps ramp up. And here's your oscillator with your ramp control. And look, right in the middle here, there's over temperature protection. So that comes in your logic. So yeah, pretty cool chip. And there's an actual schematic. This is for a 300 watt application. So this is really close to something we could use. And if you compare that to this one, this is 85 watts. There's less stuff, but when you go back and forth, if you print them off, you'll see that they're very similar. Like this one has 3 resistors in parallel for their current sense. It just makes it look more busy, but it's really just the same thing as this guy down here. The other thing is, see this voltage divider? They used the OVP and used one voltage divider for both. And up here they're saying, hey, maybe for this higher power unit you want to have a separate voltage divider for the over voltage protection and one for the feedback. So it just looks more busy. And then they added this guy here for kind of an enable function. without all that extra stuff added, you can see that they're pretty much the same schematic. Okay. And then here we are into our ratings, and here's a skip mode. They talk about, when you read about those pins up above, and then you come down here and look at this, it'll probably make more sense. Maximum duty cycle, you can go, look at that, you can go all the way up to like 94%, 94.8. That's pretty darn good. And then down here, we got a voltage reference. Here's the gate driver, and see this gate driver is capable of 1.5 amps out, and we love that because we can drive a big FET, one of these high voltage FETs, so that's great. And then just come down here to some of these curves. I'm just coming down here scrolling through this quickly just so you can kind of take a look right now. And then guys, right through here they talk about how to design it, so you can actually go through this on your own and get a good feel. And in the next video, what I'll do is I'll go through this, okay, so you can see how to design one using this chip. Or there's a lot of things that lots of parts of this, like the boost inductor selection, this design right here, that is applicable to pretty much any of these CCM type that you're going to use. Here's your input rectifier, your input capacitor, MOSFET power dissipation, boost selection. It looks busy, lots of math, but it's really not too bad. Output capacitor selection. Here's a current loop compensation. So they really give you, I think, everything you need to know to design this. It's all right here. But I'll walk you through this, and I'll do the math, and I'll show you this, and it won't look quite as busy as this. We might break it into a video where we do this loop control on a separate video. Okay, all this stuff down here, this feedback stuff, which could be kind of complicated. So anyway, we'll make it easy. We'll do the KISS method. Hey guys, so what do you think? Which controller did you like? Let me know what you think you like. I think it's a good learning experience to open up a couple data sheets, compare. You'll learn something just to look at those data sheets. Might be kind of overwhelming if you're not used to doing that, but it'll give you, it'll kind of, some stuff will soak in, and we'll talk about it. Let me know. Ask questions, and we will come back and we will go through a design, and we'll kind of try to be just concise and just say this is the steps of designing one, kind of go through it, okay? And then once we decide on that control chip, so the next video I'm going to try to come out with it really soon, and with just a walkthrough design process, okay? And then we'll end up landing on a control chip, and then we'll do the real design, schematic and everything, and come up with the actual control chip we're going to use. All right. Then I'm going to also provide some tools for you to help you with that design process for your own PFC. Okay. And so I think once we get a few more videos on this guy, maybe at least a couple more on the PFC section, then, because I think we're going to do a video of trade-offs and why would you do this versus this, and some of the questions you guys probably come up with in the meanwhile. So I think we'll do that, and then I think, after 2 or 3 videos on this, I really have confidence that, most of you guys, if not everyone, will be able to design their own PFC. All right? You don't need to know a lot of math, and I'm going to show you why. But and if you have questions about math, ask those questions too. But anyway, I think you guys will all be able to do one of these. It's just a boost converter. So, what's the big deal? Alright guys, hey, thanks for watching. 2 big thumbs up to my patrons. Really appreciate you guys. Hey, I got a new Patreon. That was awesome. Hit the like button down below. Really appreciate that. Oh, and subscribe. Most people asking questions and all that stuff, they're not even, they've been with the channel for a while, recognize the names, but they're not subscribers. So you guys, if you don't mind, subscribe. I'm just hit 18,000. That's pretty cool. But I really want to get to 20,000. I think 25,000 is actually some kind of, you know, I don't know. I think when you reach 25,000, I think YouTube helps share the channel more or something. I'm not sure about that. But 20,000 is close. Like to get there. So, oh, and there's a thank you button that YouTube added. That's pretty cool too. Another way to support the channel. And hats. Oh, and I'm going to be doing this design in a KISS analog notebook, which you can get these too. So, links down below for that stuff. T-shirts too. So, all that kind of stuff. All right, thanks guys. Hey, we'll see you next time.